Thank you. My name is Tetsuya Ogata from Waseda University in Japan. So it's my great pleasure to have this kind of opportunity to present my work. So actually, as you see now, so I'm robotics researcher and work on a combination of the neural networks and robots for over 30 years. And recently, I show some demonstrations, which can enable the robot tools and handling some complex objects. But this kind of the technique really influenced by the concept and active inference. Actually, not purely theoretically purely a copy of that kind of concept. Actually, some of the aspect is quite similar. So now I would like to enhance our model more to the more reference to your idea. And so today, I don't show not many formula, actually. So actually show the many demonstration movies. And so I hope you enjoy my talk during that movies. So here's a short advertisement of my university. So Waseda University has the longest history of the development of humanoid robots. Actually, the first humanoid robot in the world is our university developed at 50 years ago. Actually, this time, so developing a humanoid robot itself is a kind of dream. So no one thinks it's useful. Still, even now, it's not so useful, right? But it's so kind of, so my supervisor, he passed out 30 years ago, and he's kind of would like to know the human itself by making the robot. So actually, it's a very difficult to analyze the human itself. But if we develop the robot, it can behave like the humans. The robot has kind of similar functions with humans. Such kind of senses. So he told me it's 30 years ago, actually. So, and I was interested in neural networks. Then my supervisor, Ichiro Kato, he says me to you focus not just intelligence, but more emotional aspects, or finally lead to the consciousness or mind or something. So I continue that works in this 30 years. So deep learning, okay. So I now work on the neural networks, but now everyone called neural networks deep learning. So here I changed the name deep learning. So as you know, the deep learning shows a very great performance of the image processing, speech language, many types of different types of modalities. It can be handled by deep learning models. But at the same time, we know that deep learning still have the programs to, if we want to apply that was real hardware. Some of the difficulties we find. And some Altman's OpenAI CEO mentioned about blue workers last. That means the white workers, some of them by white worker is so ChatGPT seems to be becomes big breakthrough. But blue workers, the task of the blue workers is still very hard. So I think that kind of direction could be connected to the next AI. So of course there are many applications try to use deep learning for the robot systems. One of them is how to recognize object. So for example, this case is this left angle means where the robot gripper move to should go to for grasping it. So humans, designers, labels, so this kind of the rectangle to the menu object, then trained the deep learning, then automatically recognize this target, or reinforcement learning. So by repeating try and error to maximize the obtained reward, so they try to obtain the perfect model to adapt to the untrained station, something like this. But so both of the approaches still have the very big problem, so it requires huge data. So deep learning, so machine learning itself, always try to obtain some optimal best model to fitting the mapping the input to the output. Okay? So in that case, if they try to apply the robot systems, robot need to require many required to obtain the many data. It's impossible. So OpenAI used to be work on the robotics. Once they gave up to the continuous that's a project 2 years ago. So they noticed that the difficulty to then train the real robot. But recently, after ChatGPT, they restarted to the robot project because they already noticed some importance of the multimodal information. So okay, so now I'd like to consider about more human-like manner to use of the deep learning model. So in the case of the human, we don't have the perfect model for the world. Every time we have the uncertainty, so prediction error during the generating motion. For the even such an control systems to how to control the torque to keep the trajectory is a very basic way to the control the robot motion. But so for the robot engineer knows for the artificial system always have some kind of error of the real world and the internal models, and always need to control the robot to reduce the prediction error. Such kind of manner could be applied to the real robot. And some of the similar idea is or related idea to the coupling, sense of the coupling of the environment and the body and the neural dynamics. So actually, for example, passive walking model. This is just a model without any motors and computers, just a right link model. But once it's put on the sub-inclined surface, it generates walking motions without any motor and neural circuits. So the body and environment and some small neural dynamics could be generated such very complex walking patterns. So it's called sometimes called connected concept of the behavior-based robotics. So with a very good designed body and good well arrangement of sensor and actuator, it generates the motions for the cleaning room, like the Roomba or something like this. So we implemented this kind of idea using a deep learning model. So actually, in this concept, they said so we don't need to the large neural model or something like this. But now we have a deep learning. And deep learning is actually a learning model, but at the same time, it's a kind of the network to generate something. So such neural dynamics and body and environment could be coupled to generate some motion with an image processing, something like this. So one of the we developed many robots, but one of the examples that I always use this examples, and so is holding towels. Here, now he becomes this robot. So he controls this robot by using 3D mouses. And so by using 3D mouses, holding towels is still very hard problems. So conventional robot systems, so it requires a model of the towels, and it needs an image processing system to recognize the shape, and so to fit such as image and 3D modelings, and it determines which part should be grasping, and calculate the inverse kinematics, and also generate a trajectory, something like this. But we don't need anything such conventional robot systems. So now he tried to folding the towels. It takes over 1 minute in average, very hard task. But after the training, the robot can fold the task in 10 seconds. And so the point is collecting data just 50 sequences. So actually, we use 3 different types of towels and place it in a little bit different position. Sometimes change the shapes, but include all such kind of different stations. Just in total, just 50. Maybe someone use the familiar with the reinforcement learning, the robot system. It usually requires over 1,000. So we just use the 50. Okay. So this is actually a scenario when we started to make the robot to the forwarding tasks. This is a real image captured by camera. And we prepared this neural model to predict the future cognitive states of this robot. That cognitive state means one of them is an image like this, and one of them is its postures, joint angles. So now we put the towers in an untrained position. So not to include the training data. So the predicted image is not so perfect, right? So there are unclear boundary between towers and desks. So if we prepare more and more training data, of course, so prediction could be more precise, but it's impossible. So there are always limitations of the experience side. So the robot needs to generate the kinds of the new cognitive states for himself, subjective cognitive states. This is the such kind of the one of them. So this is not correct, but it's enough to reduce the prediction error as a result of the coupling of the robot and the towers and the robot bodies. Here is a dot line is teaching data, but here we should not, the robot should not use this trajectory because we put it untrained position. So the robot change its trajectory, its motions to reduce the prediction error. So perception, cognitive state in the image and the motion itself automatically changes as a result of the coupling. So here, so we use deep neural autoencoders and also recurrent neural networks to predict the future states. And maybe in short, I need to explain. So we use multiple timescale recurrent neural networks. So recurrent neural networks, but it's so predict to the different time scales in parallel. So the lowest one is the fastest models, fastest layers to predict the motion and latent space of the autoencoder to predict the future images. And next and third is embedded to the so during the training, so it's self-organized to the kind of primitive motion primitives, and lowest layer is actually kind of restriction to the activity cannot change it drastically. So it's self-organized to the order of the such kind of primitive sequences. So this kind of the representation is self-organized to reduce the prediction error through the learning processes. And this is actually results to the generate motions. So this robot doesn't have any image processing, doesn't have any 3D model for the towers, doesn't have any inverse cornering models. So no physical model, no computational model, so conventional robotics systems, just using prediction and always try to reduce the prediction errors by using coupling. Then it can handle the object. And for example, this tower is unknown. That means it was not used for the training. So in this case, the robot actually generated his cognitive state. But in that case, yeah, tower is of course predict, but the color is completely different. So for him, this kind of cognitive state is enough to generate the motions. And now we put the book, but now he predicted the towers due to his strong predictional predictions priors. So, but it can hold no problems. So this now robot has very strong priors, always try to holding everything in front of them. So if the students forget to put on the towels, the robot try to hold on the disk. Okay, so such kind of the strong prediction is keeping generating continuing these kinds of the motions. So then after developing this robot, we noticed these ideas. And very interesting. So maybe you don't need to have the explanation from me. But actually to reduce the prediction errors, there are many aspects. And machine learning people always focus on these ones. So by optimizing the weight with a huge data, the network, the deep learning model can adapt to any different types of untrained situations. But in the real actual situations, so with physical bodies, the agent can adapt to the real world by changing the cognitive state and also motion. So by changing the trajectory to reduce the prediction error. This kind of idea is very interesting. And so actually, so this sense is, so we can say something a little bit difference between the reinforcement learning approach and the active inference, I think. So actually, so the reinforcement learning, as you know, they are sometimes based on the model, sometimes not based on the model-free, model-based, but anyway, they all try to optimize the model. So this kind of the idea, sorry. So by combining the autoencoder and recurrent neural network, this is also a proposal at the context of reinforcement learning, and it's called the world models. But this world model is usually try to make it perfect as much as possible. Then in the ours obtain the perfect world models that try to find the best policy to obtain the maximum reward is searched with the trial and error. But in the case of the active inference, we know that so round model is always incomplete, not perfect. Always it has some kind of the error, prediction errors. So robots, the agent have to drastically adapt, in real time adapt to such an error by changing the internal state and behaviors. So in that case, we cannot say this motion is the optimal motion. So in this case, once a perfect world model is obtained, the selected motion can be said this is perfect, optimal, best motions in this world model. But in this case, the behavior is really influenced by the experience. Once obtained this kind of manner, so then the robot always try to everything try to fold it. This kind of phenomenon happen in human. If once the human becomes the right-hand user, then even object placed in the left side is I use the right hand. I know left hand is more closer to the right hand. But once I become habituated to this right hand, so to reduce the prediction error, so maximize the controllability, so we use this right hand. So this kind of is not so phenomena happen, but it's still very important. So to apply the learning model to the real robot system. So from now, I show some demonstrations. One of them is opening zipper. This is one of the very difficult task for the robot systems because now starting from the grasping and zippers, then handling conditions always could be changed, and also the according to change of the torque, the robot need to change its trajectory, not just change the torque. It needs to change the trajectory. That kind of sense is very important. But everything is done by for reducing the predictive error. So teaching is like this. So in this case, we just do 36 teaching data. That's enough. And after that, this is a scenery for the opening the zipper. This is a captured image, and this is a predicted image. And this red point is an attentional point. This is a very interesting demonstration. Now he seems to be a little bit confusing. And so the changes to the trajectory with a trial and errors and the final opening. So this kind of motion automatically generated. And again, back to these attentions. So actually, this predictive coding idea, so there are the idea of the precision of the sensory precision or prior precisions. So precision now is, I think, corresponding to the attentions. Then the attention, of course, is common in the deep learning peoples. But for the attention, the image, usually the deep learning, so they use only the image for finding the attentional point. But in these cases, we try to make the attention to reduce the prediction error. In that sense, so the attention is generated for the attentions. So For example, so I don't enough time to explain the all, but so the target is how to reduce the prediction error to the all cognitive state. It includes the image and the tactile senses and the motions. So the propagated and trained to these networks, but the networks have some trained to select some high precision point. This point is trained to reduce the all prediction error. That is I think the connected to some kind of the idea of the sensory precisions. And sorry, continue this movie. So this is another example. So by changing the lighting condition, it can adapt to it can continue to the work. And so this is a very symbolic scenery. So here, the robot can adapt to the change of the position of the object. But so this one is a real exact camera image. And this is generated his cognitive state. And you can see to reduce the prediction error, his cognitive state now the other object is disappeared. So by adapting the internal state, latent state, so that now we can see as an image as a latent space. But anyway, so by adapting the cognitive state, the robot can to the adapt, continue to the work in this kind of the task. And so we already started collaborate with some industrial company in Japan for this idea. And so some of them is show the demonstration 6 years ago, and some of them is already released as a product 2 years ago. So the target is some very with a complex characteristics in physics, like how to measure the powder, how to measure liquid with viscosity, something like this. So this kind is a target a little bit hard to the modeling, but by using such a prediction learning models, the robot can handle it. And this is the product. And this one is also won the ICRA best paper award 2 years ago. So this one is how to the handling this kinds of food. So interesting that this robot firstly try to actively physically interacting with the material to recognize the object characteristics, and after that the robot can select the tool and pouring it. The pouring motion itself is very difficult. But so by using always predicted to the future stated, so the internal latent space is determined, then the motion can be generated. This is a training object, and this is untrained object. Then after that, so deep learning is always said in the black box. Yeah, actually, some parts of black box, but we can analyze some of the level. For example, in this case, we can analyze an activity of the recurrent neural networks after the touching. Then by applying the principal component analysis, we found these spaces. So the networks. So after that, active recognition, active cognition. Then is each object cluster like this. And also there are some boundary to which tools should be selected. And this one is if we put in the untrained object, so each object seems to be separated correctly. So the object is recognized not by vision, just not one image, but interacted. So by predicting some dynamics as a cognitive experience, then the object is determined, recognized. Yes, this is a comparison result in the case of which type of the information requires. So finally, you found that the image and the force and tactile and every information is important. But actually, this is a very hard task. So there are many cases with failed, but so by combining such a predictional control, then the robot can be change its manner so to reduce the prediction error. Then the robot can and also goals and then robot can handle the object like this. So I showed many movies. Then the other example is so finger hand. So hand itself is originally developed. The first human-like hand developed at 1964 at Waseda University before I was born. And so there are also many good tactile sensors. So already developed. But so in this case, this robot has almost 400 tactile sensors. But so with that hardware, we don't know how to control it. But so now we can use so such predicting controls. So robot you can see the robot controls and object handling, even this kind of different types of object. And so in this case, we don't use any image cameras. And if humans interrupt like this, but so the robot can recognize it and automatically generate this kind of motions. And another one is door opening. Maybe the next movie might be good. Maybe some of you know him, so Jensen Huang, the CEO of NVIDIA. And yes, we demonstrated this robot, executed this robot at 5 years ago, 2018. But then published the paper is 2 years ago. It takes 3 years. But anyway, so Science Robotics is one of the top journals in the robotics area. And you can see now our model can enable the control the whole body. Robot whole body control. So even a vehicle control, everything is every motor is controlled by our predictive model. So no conventional robot systems. So you can see the very stable motions, even the pushing and pulling. So and also even the human interrupt like this. So then always try to reduce the expected the error of the expected conditions, predictions. So then robot can continue this kind of motions. Yes, this work is selected in the cover of this issue. So in this case, we use so multiple prediction models. Actually, 6 prediction models for the close to the door, open the door, and passing the door, and then opposite side. And each module try to predict the future state. And the module with the minimum prediction error is selected as a controller for a whole body. Okay, here is so far is just an application. So I hope you can a little bit feel some potential of so such a predictional model to enhance robot abilities in future. But the current models we used only this part. How to reduce the prediction error. That's it all. Very interesting. Even this kind of path is shows this kind of them. But we don't think we haven't think that this part so handling how to reduce uncertainty. So we try to enhance our model tools including this target. For example. So now I'd like to show the very preliminary study compared to the other my robot studies and explained so far. But I think that this kind of the model research is very important to enhance our models, our robot applications. And this is publishers and scientists report, and the targeted sensory attenuations. So we recognizing sensory information. So generated by myself is not so important, but generated by the others is very becomes sensitive. So how can we explain this phenomena by using the free energy principle? So actually, some of the explanation computational models could be considered. One is a forward model account. So actually, before this paper, I think I thought that this is might be one of the explanations. So that means so efficiency copy some of them, so the brain generated the motor command. Then we can, that command could be used for the canceling such a sensory information by generated by myself. That is quite very control system as an explanation. But so other explanation could be precision. So sensory precision could be becomes increased during to generated by myself. So how to replicate it, this kind of phenomena using the robot system. So this one is model. So this is actually robot. But now it's used for just collecting the training data. So actually, they are experimented done in the simulation like this. And this is a model, maybe as I explained later. But so we set it to two conditions. This one is visual information, sensor information, and extraception, proprioception, so that is motion is fitting. And the other condition is a little bit changed. What happens in the activities that this sensory area we try to confirm. And this model is trained with the form of following these equations. So one is actually this is the process how it works. So the first term is to solve how to reduce the prediction error. And this is how to reduce the prior and posterior error distributions. Okay. So this is come from priors come from each layers as described in the zetas. And so D is a recurrent internal states. So during the learning process, so the network tried to minimize this F by changing the weight and also updated the Q zeta. And actually, for the processing, so given to the Q zeta here, priors, and also then of course internal state is calculated, then generated the motion. And so networks and internal sensory activities, we can observe it. So this is the result after training. So actually, this is a case of matching to the vision and the actual motions. Okay. So in this case, you can see zeta one is here. This sensory state. So in this case, is to minimize the free energy. So this more middle layer, the higher layer is activated. So that means the prediction. So more higher level prediction is fit, and so but once it changes to the gaps to the sensory mode, visual sensor and real motions changes. So you can see that this the lowest layer, so the sensory state is activated. This kind of manner is self-organized, without any such this kind of the feedback. Just we train the network to reduce the free energies, and try to generate the motion. Then these kinds of the motions, this kind of the phenomenon is appeared. And this one is actually is how to update it this posterior and priors. And so actually during the generating of motion, we prepare some windows and using back propagation update it. So back propagation, of course, basically used for the learning for the weight. But in the actual the running processes, this back propagator error is updated in the prior. So that means it requires a huge computational cost. So this model is very interesting to sense of that which could handle the uncertainty. So uncertainty. So for example, so if we use just only the prediction error, the door opening task. So in these cases, so strong prediction is okay. So the robot already knows the first it should be pushing and the secondary pulling. So prediction is always correct. But sometimes we need to confirm that it is pushing or pulling. Okay. So prediction is sometimes should be some we have the weakness and so more uncertainty to increase. This kind of some of the how can I say uh, try and error motion, something like this. That is so required to the second terms, how to your prior is more precise or not. So in that kind of sense, so we should apply this kind of networks model for future robot systems, but still hard as again, so as I said, so it requires huge computational costs. These versions. So now some of my colleagues try to improve the models. Okay, so I'd like to use a small time to the end of my talks, and so introduce this project. Sorry, this is a very good opportunity. So now I'd like to enhance our AI robot system to the more general purpose robot systems. And there are the big projects supported by the Japanese Cabinet Office called Moonshot. Moonshot means it comes from an Apollo rocket project in the United States. So the president said, and we will go, we take the humans to the moons in the end of the 60s or something like this. So we prepared some such kind of the goals, in total 9 goals. And goal 1, goal 3 related AI robotics. And now we joining the goal 3 and try to develop such kind of smart robots. So as I mentioned, so Sam Altman mentioned about the Moravec paradox is one of the biggest problems. So the current deep learning model, which requires a huge size of data, is not suitable for develop such kinds of robots. So I believe that our technology, techniques, so by referring to the idea of the active inference, might be a very good approach to develop such kind of robot. And now, so there are many different types of robots. Which target completely different. But I believe that this kind of the robot could be merged to a more general purpose. So as like same as a smartphone. So you can see there are many devices so far, but finally it's packed one device. Then it can serve the new kind of the values. So and this is a robot science we developed by using our models. And cleaning, cooking, washing, so this kind of target, always, so we investigated these many countries with questionnaires of their requirements. And this kind of task is every country is needed. And so this one motion is generated by our predictive learning models. And here is I'd like to show you some interesting examples and cooking the scrambled egg. So this is one of the difficult targets because during the cooking, the condition of the egg is changed. First, it completely liquid, but now becomes solid. So a robot needs to recognize the change of such kinds of target conditions and change its strategy. So as you see, is actually this caption is we labeled after the training, after observed generated motion. We didn't design it. So in this case, C taught the robots the cooking 20 times or something like this. Then he cannot explain how to cook it. But we could analyze so it seems to be changes and precision of each modalities. So firstly, it mainly focused on the visuals. But during the cooking process, the attention moved to the more tactile on the torque. So at first I said that it's okay just starting randomly or same manner, but if we do so, then the result is like this. So we cannot eat. So by changing the strategy to recognizing the object dynamics, then robot can cook correct. So maybe I still have the time, but almost end of my talk. So now we release an open source software for this our predictive models. So it includes such attention mechanisms. Of course, if you have some interest to then please use it, or give us a comment to improve our models from the viewpoints of the active inference researches. And final one is example is collaboration work is JAXA, Japan Aerospace Exploration Agency. So as an opening jipper, this kind of motion is as far as we showed just a demonstration, but this kind of work really important in such a work in space stations. We supported such kind of task by using this robot. Now then collaborate with JAXA, then started developing this robot now. Okay, so maybe sorry that the control, my time control is not so correct, but yes, that's all most of my talks. Thank you very much.